Good day, everyone. Welcome back to Learning to Understand Digital Electronics. Today we're going to start off with adders. Now this is a big and complicated topic, so we'll cover subtractors in the next video, and the video after that we'll cover not parallel, but adder subtractors. Now, the first type of adder we need to understand is a half adder. What does a half adder do? Whoop, delete that. So half adder. Uh, Once again, I made a mistake. Whoopsie. Adder. So, half adders allow us to basically just add any two bits. So, we're going to have an A input and a B input. And then this block will take in our A, it'll take in our B, and then it'll give us an output of our sum and our carry, which we call Cout. So if we were to actually put this in a table, let's see this in practice. So I have an A input and I have a B input. Then I have a sum and I have a Cout. Now I'll have 0, 1, 0, 1, and 0, 0, 1, 1. So when we add these two zeros together, we'll get a 0 output, and we're not carrying anything over. So Cout is our carry. So we get a 0 plus 1, that gives us an output of 1. Now that gives us no carry as well. Same for A plus B gives us 1, no carry. But now A plus B gives us a sum of 0 and an output of 1. Because you see 1 plus 1 gives us 2, which is 1, 0. Now, if you actually look at these two types of gates, you'll recognize that this is a XOR gate, and that this is an AND gate. Because the AND will only be powered when both inputs are 1. And the XOR gate, or exclusive OR, will give a power only when the two are different. Because the second we add two ones together, well, we're going to get a carry. So when we actually draw our circuit of this now, we will get our A line, our B line, and this will go into an exclusive OR coming out, and then our B will come down, our A will come down, and this will go into an AND. Oop, that is not very round. So this is going to give us an AND. So this will be our sum output, and it's going to equal to, if you remember, the formula is A, B inverse, plus A inverse B. Now, a shorter way to write this is we're going to say A, circle with a plus in it, and then B. That's just going to save us time while writing. So whenever you see me writing this, it's going to be A, B inverse plus A inverse B, which is just short for an exclusive OR. So then this is our A input, this is our B input, and this is going to be equal to A plus circle B. And then this is just going to be our carry or our C out, and that is going to be equal to our AB. Now, you notice the problem here is we can add 2 bits. We can add 2 bits by themselves. What happens if we want to add multiple bits? Well, we'll need a more complicated adder. But if we take, let's say, 1, 1, 0, actually no, let's say 1, 0, 1, so that's 5, plus 0, 1, 1, let's say. Well, this is going to give us an output of 0, right? But then you notice we have a carry. And that's going to give us 1. No, that's going to give us 0. And that's going to give us a 1. So you notice, though, that this gets carried and this gets carried. Now, we could add these 2 bits together. We could add these 2 bits together. But in order to actually make all these adders actually work together, we need to find a way to actually input this carry bit. So we need to find a way to take in not 2 inputs, but a third input called our carry. And that's where we get something called a full adder. Now this has its A input, its B input, but now it also has a C input for carry. And then it has its output. So we have our A input, our B input, and then we have C in. And then we're going to have our sum, and we're going to have our C out. We're going to have our C out. Now let's create the table for this. Since we have 3 bits, input bits now, it's going to be a much larger table. It's going to be A, B. I'm just going to say CI. And this is going to be our sum, and I'm just going to say CO because it's very hard to write this on a whiteboard with a mouse. So this is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. Oh no, sorry, this is going to be 1. It'll be 1, 0, 0, 1, or 1, 1, 1, 0, then 1, 1, 1. So there we have all of our input combinations. And now, just like this table, we are going to add these all together and get our carry. So this is 0, and we'll have a 0 carry. And now, this is a carry of, this will be a sum of 1 and a carry of 0. This will be a sum of 1 and a carry of 0. But now we have 2 1s. So this will be 0, and we'll get a carry of 1. And now, we have 1, 0. And then we have 2 1s, which gives us 0 and 1. 2 1s, which give us 0 and 1. And then we have 3 1s, which will give us a 1 and a carry of 1. Now, we need to figure out a way to put this into formulas. Now, unlike with a half adder where we can just immediately recognize this, we need to actually figure out our formulas. Now, what I want you to do at home is do a K-map calculation, just like we discussed in the last video. So every time the sum is equal to 1, you're going to take this value and you're going to take that value, this, no, the one, you're going to take this value, and this value. And you're going to plug all of those into a K-map, and then you're going to solve for it. And then you're going to do the exact same thing with your Cout, but now you're going to look at the values that'll give you an output of 1 for Cout. So it'll be this one, this one, this one, and this one. So you'll end up with 2 K-maps, and you'll solve them. And your answers that you should get, whoa, why did that move like that? So now, once you've done your K-map, you should get your equations for your sum, and it should be equal to A inverse, B inverse, Cn plus A inverse, B, Cn, invert, plus A, B inverse, C inverse, plus A, B, Cn. Now, this should be the simplest equation you can have. But now, there is a nicer way to write this. So I'm going to show you the proof, because this also took me a while to figure out. So we're going to group our C's together. So we have Cn, and that's made up of an A inverse, B inverse, Cn, no, sorry, Cn is going to stay there, B inverse, and then it's going to be plus AB, and then this is going to be plus C inverse, and this is going to be A inverse B plus B inverse A. Now, one thing you may notice, this is that this is an exclusive NOR, which is actually the inverse of this, because this is an exclusive OR. So this is the inverse. So if we cross that out and we would put A, I'm just going to do the circle to save time. And then we put a thing over there. You'll notice that our one term for Cn is inverted on this side, but it's not on this side. While this term is inverted on the same side as the Cn that's not, and the one that isn't inverted is on the side that has the C invert. Okay, I might have explained that a bit badly. Just to reiterate, this is not inverted and this is inverted, while this is inverted and this is not inverted. And if you're looking closely, that will remind you that this is just a XOR gate, an exclusive OR. So what we're going to have is in our sum can then be described as our sum can be described as an exclusive OR going into an exclusive OR. So this is A, this is B, this is C, and then this will be A, and then we're going to actually make that exclusive. So this is going to be A, B, and then we're going to write this as this, because this is the input and this is the other input. And because of how this is, you could do this with any of them. So this is inclusive. I can't remember the exact mathematical term, but you can change these around. And if you want to prove it, try and convert this back down to here with using B as your main one, or C as your main one. But we're going to keep C as our input line for a very particular reason. So that is now described our sum. So now we know our sum is equal to this. Now, I hope I explained that all well. So we have two exclusive OR gates that describe our sum. And now we're going to look at our Cout. Now, once again, if you did a K-map, you should get the values of A, B, plus A, Cn, plus A, plus B, Cn. Now, once again, just like with this line here, technically you could put this in a sum. You could put this into like all these gates combined. The only thing is you don't really know, because sometimes you can have something like this and it won't be able to be simplified down into two gates, because this is the simplest possible combination of it for a K-map. So these XOR gates are very special because they are sums of products already. So a K-map can't simplify down into these things. So occasionally you will get a scenario where this is your simplest normal expression, but then because of how XOR gates work, you can sometimes simplify it down. Now, that's not going to be for every case, but for these cases it does work. Now, when we look at our AB, ACN plus BCN, well, if we actually go and this can be rewritten as A, B, Cn, because our B, and this can be A, B inverse, because remember, this is the missing term. And if I were to combine these back together, I would get ACN bracket B plus B inverse, and B plus B inverse, as per the laws of Boolean, is going to give 1. So why am I expanding this again? Well, once again, there's a better way to simplify it using exclusive OR gates. So this could be A, B, C in, this, and then this could be A inverse, B, C in. Now, we have two of the same terms, which means we can cross that one out if you remember your laws, because they're both going to give the same value. And now this is AB and this is ABC in, so they both share this AB, which means that I can cross that term out. So then we'll just be left with AB, ABC in, AB inverse C in, and A inverse BC in. And you notice AB is inverted. Once again, you'll see if you look at those two terms, we'll get an exclusive OR gate. And this will be A. So not every single time will things simplify down into exclusive OR gates. It's just because of the nature of these sort of adders and stuff that they do, and the exclusive OR gate special properties that work well with these. But you get a random K-map and you get something, you're very likely not going to be able to simplify it down into exclusive OR gates. So you probably shouldn't be just trying that always. But I'm just trying to help you to understand these things. So when we look at that, we have our AB gate, which is an AND gate. And then we have our C in times AB output. So it's going to be this AB. We could draw a new gate, but since we already have a gate here, we're just going to do this. And these are both AND gates, and then we're just going to add them together. So this is going to be A and B, and this is going to be C in A plus B. And then that's going to give our C out, which is just going to be AB plus C in AB. So this is what our full adder completely looks like now. And if I go and grab some other colors, let's grab maybe green and blue. If I go and highlight this, now it is a bit higgledy-piggledy, but you notice there is a XOR gate and there's an AND gate, and they both go towards the output. So if you go and look back, that looks very similar to this. It has two inputs, XOR gate and AND gate. So that is a half adder, and we're going to call that half adder 1. Why is number 1? Well, what do we have here? We have another OR gate, XOR gate, and Yeah, that is very messy. Sorry about that. But you notice this has two inputs, and these two inputs then drop down. The input for there and there both drop to go there. So two inputs, and they both go into an exclusive or XOR, and they go into an AND gate, which means this is also a half adder, and that's half adder 2. And that's exactly why they're called half adders, is because we use two half adders together to get a full adder. And when I actually go ahead and redraw the circuit, like without the gates and stuff, you'll notice if I draw with half adders, um, so if this is a half adder 1, this is input A and input B, and this is my sum, and this is my C out. And then this will be my C in, and then this will be my A input and my B input, although now my A is the sum of the previous half adder, and my C out, and my B will be the value of my C in, or my carry. Now, that will give me my total sum out, which comes from my sum here, and then my C out. And these two carries are added together to get an output. And that will be my total C out. So that's how a full adder works. It takes two half adders, which allows us to basically add 3 different bits together. And by carrying our sum over and adding up our C outs, we're able to add 3 bits. And that way we can actually carry these carries around. So now we'll go to the final bit, which is the parallel adder. So parallel So how does this work now? This works by using the full adder, and now we actually string them together to get this. So you get 2-bit adders, 3-bit, 4-bit. I'm going to keep it simple today. And just for the sake of time and all these sort of things, I am a bit lazy, I'm not going to lie. I'm going to do a 2-bit. So we have our one full adder and our second full adder. And this is going to have the 2 bits. So this is going to be A1 and B1. And this is going to be A0 and B0. So that means this part here are the LSB. Now, since this is a full adder, I need a carry. So I'm going to say my C in, and there's my sum. And then I take this as my C1. Now this will be my sum 0. This will be my sum 1. And then this will be my C out. And this is a full adder. And this is a full adder. Now you're wondering, okay, but now we have to have 3 inputs in. What? Now we're only adding 2 numbers. What's Cin gonna be? Simple. To keep Cin out of trouble, make this equal to 0. Just make Cin equal to 0. Because then it literally does not add to the sum and it does not add to a carry. So then Cin doesn't really matter. So if we were to take value of 1, 1, and 1, 0. So this is our A0. This is our A's. This is our B's. Now let's first do this by ourselves to just see. This will be 1, and that'll be 0, and we'll get a carry of 1, and we'll get 101. So if we plug in a value of 0, and then we go, then we make B equals 0, and A equal 1. Well, 1 plus 0 plus 0 gives us a sum of 1, and then we have a carry of 0. And now A1 is going to be 1, B1 is going to be 1, and then C is going to be 0. So 1 plus 1 gives us 0 with a carry of 1. And you notice there is our number with our LSB and our MSB. So basically you just take this and carry it off. And that is pretty much the entirety of adders. Now, when we get to subtractors, it's going to be slightly different because we're now subtracting. And then the thing is though, subtractors is more for just knowledge base because we don't really use them in real life. We'll use the thing after that called an adder subtractor word for reasons we'll get into in the next video. Okay, thank you for your time. I hope you enjoy your day.